5 here. Considering that the limit of the expression 2x plus 3 as x approaches 1 equals 5, we're going to find the largest value of delta such that the function value, whatever 2x plus 3 is no more than 0.01, actually less than 0.01 units away from 5, whenever the x value is less than delta units away from 1. So we want the delta that we find to make this happen. So let's kind of start with that and see if we can express absolute value of x minus 1 in terms of a number that will work for us. So I like to begin with this expression, the absolute value of 2x plus 3 minus 5, and just kind of work on it a little bit. Simplify it, see what it looks like. If we clear the parentheses and then subtract 5, it's going to look like this. Absolute value of 2x minus 2. And then if I'm going to throw in that extra step. I'm going to factor out the 2. Actually, it boils down to 2 extra steps. Not a big deal as long as the slope of that linear function is positive, but when the slope of the linear function is negative, sure don't want to go factoring out a negative 2. That doesn't make sense. And then there's the question about where the negative sign goes. So the absolute value of a product is equal to the product of the absolute values. Basically, I'm using the fact that the absolute value of AB is equal to the absolute value of A times the absolute value of B, whatever signs A and B might have. This is a true statement. So this is the absolute value of 2 times the absolute value of x minus 1, and then the absolute value of 2 is just 2. That's why we can factor out the 2, and it looks like that's what's happening. So this is 2 times the absolute value of x minus 1. Now, we want this expression to be less than 0.01. So we want absolute value, 2 times absolute value of x minus 1 to be less than 0.01. So it looks like that's going to happen when the absolute value of x minus 1 is less than what? Whatever 0.01 divided by 2 is. So absolute value of x minus 1 is less than 0.005. Okay, so it looks like delta equals 0.005 works. And by works, it simply means that whenever x is within 0.005 units of 1, then f of x, 2x plus 3, is within 0.01 units of 5. Now, show it works. No, the homework problem didn't say show it works. It just said find the delta. But if we find it, we want to be confident that it actually does work. So to show it works, it looks a lot like what we just did. It's going to feel like deja vu, but really what we did is just kind of scratch work. Now we actually want to show that it works. Suppose 0 is less than the absolute value of x minus 1, and that's less than 0.005. Let's just make this assumption. We want to show this. We want to show that based on this assumption, as long as x is where it needs to be, 2x plus 3 minus 5 has absolute value less than 0.01. Sorry. So let's show it by beginning with the expression and then demonstrating that in fact this is less than 0.01. So I don't want a less than sign there, sorry. I apologize if you're using pen. I want an equal sign there. So kind of just what we did, but I'm going to skip a couple steps so it doesn't seem quite so tedious. This equals the absolute value of 2x minus 2. Based on what we did over here, this equals 2 times the absolute value of x minus 1. Now we're assuming this right here. So we've got to use that. If we don't use that, then what we're concluding would be always true. It's not always true, but it is going to be true if absolute value of x minus 1 is less than 0.005. So we've got to use this. If this is true, so off to the side, maybe over here, absolute value of x minus 1 is less than 0.005. What happens when we multiply both sides by 2?
Or 0.
Yeah, there we go, like that. So if we have this expression here, based on our assumption, this is less than 2 times 0.005, and that's equal to 0.01. So sure enough, absolute value of 2x plus 3 minus 5 is less than 0.001. And that concludes that. One more of those homework problems, maybe with an actual epsilon and an actual delta. 7. Use the formal epsilon delta definition to prove that the limit of 4x plus 1 as x approaches 2 equals 9. So given some arbitrary epsilon greater than 0, we need to show that there exists some positive number delta such that absolute value of 4x plus 1 minus 9 is less than epsilon. Last time we talked about if 4x plus 1 is approaching 9, eventually it has to get really, really close to 9. You can't approach 9 without getting really, really close to it, eventually. So 4x plus 1 is approaching 9. Well, how close do we want it to be to 9? Well, let's say it's got to be this close. This close. It's got to be within epsilon of 9. So the difference between 4x plus 1 and 9 is less than epsilon whenever absolute value of x minus 2 is less than delta. Now, we put in this 0 is less than basically all the functions that we consider, unless I just make up some off-the-wall piecewise function for us to spend some mental gymnastics with. Most of the functions we consider are going to be continuous functions, so that they're going to be defined at this particular point, and they're going to be defined to equal the value of the limit. So the 0 is less than really is not going to come into play all that much. But what it's saying is that this doesn't have to be true exactly at x equals 2. It just has to be true really, really close to 2, when x is really, really close to 2. But the 0 is less than turns out not to come into play very much for the examples that we consider in this class. All right, so scratch work. Find a delta. Find a delta that works. So here we go. Absolute value of 4x plus 1 minus 9. We need that to be less than epsilon. So we're going to have control over this expression, absolute value of x minus 2. So we're going to try to express the absolute value of x minus 2 in terms of epsilon somehow. So we simplify. This is the absolute value of 4x minus 8. That's got to be less than epsilon. Now, there's two steps I'm going to skip. Factor out the 4, use the property of absolute value, and then eventually the 4 comes out in front, and we have 4 times the absolute value of x minus 2. We want that to be less than epsilon, so that means that x minus 2 really needs to be less than what? Epsilon divided by 4. So we need that to happen. Well, in order for that to be true, let's let delta equal epsilon over 4. And now for the actual proof, show that delta equals epsilon over 4 actually works. So we got our scratch work. The scratch work produced a delta. So we think maybe, yeah, if we decide how close 4x plus 1 needs to be to 9, then divide that by 4 and make sure x is no farther away from that than 1. So show that epsilon over 4 actually works. So suppose 0 is less than the absolute value of x minus 2, and that's less than delta, which we are going to let equal epsilon over 4. Suppose that's true. We're supposing that, but we've got to show, oops, that's not red. We've got to show this. Once we show that, that's the punchline. We're done. So here goes. What can we say about the absolute value, wrong shade, absolute value of 4x plus 1 minus 9? I want to show it's less than epsilon. What I know is that it's equal to the absolute value of 4x minus 8. It's equal to that. I know we can factor out a 4. So it's equal to that, because 4 is positive. And off to the side over here, somewhere inside our scratch work, more scratch work. I'm not going to try to draw a bubble. Maybe a scratch octagon. That's going to be rough looking. How many sides does that have? Is that a nonagon? Anyway, whatever shape that is, what we need is this. Suppose we know the absolute value of x minus 2 is less than delta. That's what we're assuming. What happens when we multiply both sides by 4? Four times the absolute value of x minus 2 is less than 4 times delta. That's kind of key. I found in the past that's the hardest step in the entire process for students to see when I have this and just jump down and say that. It's different looking at it vertically than it is horizontally. Horizontally, I think it's clear. We have absolute value of x minus 2 is less than delta. We're assuming that. Multiply both sides by 4. What could be clearer than that? Multiplying both sides by 4. But here it's like we got a top and a bottom, and we multiply the top and the bottom by 4. The way they're arranged there on the page. I think it's just the way they're arranged on the page. If that's the least bit tricky to see there, I think it's just the positioning. What's delta? Epsilon over 4. And 4 times epsilon over 4 equals epsilon. Rough looking epsilon there, but there it is. So that's the conclusion. If x is less than delta units away from 2, then 4x plus 1 is less than epsilon units away from 9. And that's that proves it. There's a more complicated looking argument, and in my opinion, a good bit more interesting. But there's the fear of getting bogged down because there's so much to do in this class. I don't want to spend any more time than absolutely necessary on this.
So your answer is epsilon?
Well, the answer. Well, we assume this, and then we showed this. And in fact, if you want to, you can kind of string these off to the side. But basically, since this was what we needed to show based on our assumption, we've kind of showed it. So, yes. See, what are we trying to show? We're trying to show the limit of this expression, 4x plus 1 is equal to 9. Mm-hmm. So we just want to make sure, can we make that as close to 9 as we please by making sure that x is close enough to 1? And here, you tell me, how close, let's pick an actual number. How close do we want 4x plus 1 to be to 9? How close? This close? That looks like what, about 0.08? Yeah, 0.08. That's how close we want 4x plus 1 to be to 9. Well, if I guarantee, if I choose any number that's within, what's 0.08 divided by 4?
0.002.
So like 0.08 divided by 4 equals 0.02. So as long as I choose a number that's no farther away than that from 1, when I evaluate the function, I should get a number that's within 0.08 units of 9. That's what we're saying. So let's pick a number that's no farther away than 0.02 from 1. What's such a number? How about 0.985? Is that close enough to 1? Is that within 0.02 units of 1? What if we evaluate our function? I know I shouldn't require the use of a calculator to do this, but it's paid for. What if I say 4 times 0.985 plus 1? Is that going to be within 0.08 units of 9?
1.98.
Yes.
1, yes, thank you. What's the deal? No.
Problem comes in when you use a
2. I was thinking that was a 1. So the proof was correct, but
1.95.
gosh, wow. 1, thank you. Yeah, it's got to be close to 2. Well, thank you all for nodding and going along with me. Yes. 4x plus 1's got to be close to 9 when x is close to 2. So that's better. Let's try it again. What happened there? All right, never mind. 1.985 plus 1. How close is that to 9? That's within 0.08? Yes. All right. I don't know if that helped at all. But I meant well by it. I'm just saying that if x is close enough to 2, then 4x plus 1 is guaranteed to be as close to as 9 as we desire it to be.
So pretty much the answer to the question is everything, pretty much that little section that says, well, everything from suppose to equals epsilon.
Right.
That's
Mm-hmm.
the answer.
This is the answer, right?
That's the answer in the end.
Okay.
Yeah, that's the answer.
I think that was your question.
Yeah.
I feel like I can figure out the answer to the question, but I'm still really confused on everything you just showed us on the calculator and everything.
It's probably best that I don't do the souped up version where it's a quadratic function rather than a linear function. because there's considerably more to think about there. It's really interesting, I think. When you see this problem on the test, it will look like either 8 or 9. It's much nicer when all the blanks are there for you. Let's do maybe one more of these, and then we will move on. Section 2.3. We want to show that the limit of 3x plus 5 as x approaches 2 equals 11. First, does it look like it does? If x gets really close to 2, then 3 times x is going to be really close to 6. And then 3 times x plus 5 is going to be really close to whatever 6 plus 5 is, 11. So yes, it looks like that's going to be the value of the limit. Now find delta in terms of epsilon so that this is going to happen. What's a good bet for the value of delta in terms of epsilon? We need to go through the process. We would say something like this, and something like 3x minus 6. Absolute value of that is less than epsilon. And then factor out the 3. We can do it since 3 is positive. And in order for absolute value of 3x plus 5 minus 11 to be less than epsilon, absolute value of x minus 2, we need to make sure that's less than what?
Epsilon over 3.
Epsilon over 3. So however close we want 3x plus 5 to be to 11, x needs to be
less than epsilon over 3.
Yeah, less than a third of that distance. So there we go. Delta equals epsilon over 3. Now, assume that it is. Assume that the x that we're thinking about, x is within that delta, epsilon over 3 units of 2. And if it is, then this is equal to the absolute value of 3x minus 6. And that's equal 3 times the absolute value of x minus 2. What goes next?
Less than epsilon.
It's less than 3 times. I'll go ahead and throw the delta in there, but if you want to put the epsilon over 3, that's fine. So this equals 3 times epsilon over 3, and there we go. So basically the substance of the proof is found right there.
So you're just proving.
Yeah.
Yes. Where exactly do we ever actually use the 0.4 at any point to, like, I don't see it seems like we don't ever use it. The given epsilon equals 0.4.
In problem 8?
Yeah.
Let's see. In problem 8, you express the delta in terms of that. What's going to happen?
Oh wait, I'm looking at the completely wrong problem. I was following on the wrong scale.
Oh, yeah. Yeah, you use it in problem 8, but you don't use it in problem 9. Yes.
On the first page of the homework, to do with filling out the chart, do you use your graphing calculator?
Yes.
To graph the equation?
Yes, absolutely.
Okay.
Yeah. That would be problem 2. All right. Yeah. Yes.
That's how it would be presented on the test.
As far as the epsilon delta, or the table,
problem that we just saw.
the one that we just saw. Yes, it's far easier for me to grade that way, and I think it still gives you the idea of the logical progression in the thought. So I do give you a lot of blanks to fill in on the test. All right. 2.3 then. I may not have enough of these for everybody. Let's see. Were you able to get a copy? No. Let me see how many I have left. Was anybody able to find a copy of 2.3? You did.
I got it like half.
And you did. Awesome. Now let's see what we've got. Y'all get a copy of 2.3, 2.3. You got one? Like one? Anyone else for a copy of 2.3? I don't mind making another copy if I need one. I just made. That's fine. I just made 16 copies in the hopes that one or two folks would have them. One more? Going once? Going twice? All right. I'll keep it in case I need to refer to it. (2.3) Evaluating limits analytically. We need some basic rules. Now, for these limits, it's possible to use the epsilon delta definition of limit to prove some of these, and perhaps I should actually try to use it for, or maybe one of these, but for some of these it can be quite a challenge. So rather than do that in each case, we kind of take time away from other things that we need to be doing. We'll just use some intuition and trust those calculus experts that have gone before us as far as some of these limits. Let's use some intuition on the very first one here. Limit of a constant. If you want to think of this as being the limit of a function defined to be a constant, you've got the graph of a constant function. Basically, f of x equals b. Goes to the point 0, b, and its graph is a horizontal line. If x is approaching, I don't know why I went with a there and c in the other two, but I guess I'll leave it. No particular reason for the choice of a versus c. If x is approaching a, like this, and like this, we can ask ourselves, I mean the point in question is right here, it's actually a solid dot, but I'll just represent it as an open circle. We can ask ourselves, as we consider points that move along here with x coordinates that are approaching a, and points that move along here with x coordinates that are approaching a, the y coordinates of those points are constantly b all along through that process. So although it seems if you're just kind of hanging around at b in everyday life, we don't say we're approaching b. If you're hanging around at the pool hall, people don't say you're approaching the pool hall, you're just kind of there. But that's what's going on in this case. Literally, it fits the definition of a quantity that's approaching b. If we pulled out the epsilons and deltas, that's what would be the case. So the limit of a constant equals that constant as x approaches any number in the domain of that constant function. Let's look at the second one. A little bit more interesting, perhaps. The limit of x as x approaches c equals c. So we've got the identity function here. Almost got it right. Try it again. The identity function. Okay. Y equals x, or f of x equals x, and x is approaching c. Well, we've got some numbers along the x-axis that are approaching c, and approaching c here. So the x value is approaching c. Consider the point in question right here. This is c as it's represented on the y-axis. And consider the corresponding points along here and along here as x approaches c. What do we say the y coordinates? What does it look like the y coordinates of those points are approaching? Well, all along here you have points where the x and y coordinates are the same as each other. So as the x values approach c, the y values also approach c. So the limit of the identity function as x approaches c is equal to c. Would you feel better with an epsilon delta proof of this? Or is it sufficiently intuitive as it is? I think we can do one, but I think we'll skip it nonetheless. I'd really prefer not to try an epsilon delta proof of this next one. The limit of x to the nth power, not even going to go with the picture, but if we can just use some intuition here, as x gets really close to c, based on what we know of functions of this nature, then the y coordinates are getting really close to whatever c to the nth power is. How do you feel about that? The textbook didn't offer a great deal of proof of that, but we'll accept it. And there's actually a little bit. There's another theorem that appears down below that we can actually use that to come back and shed a little bit more light on this one. Perhaps we'll do that in a moment. Oops. Yeah, let's go here. So example 1, some kind of trivial ones here, but we'll run into this sort of thing. It gives us some ways of evaluating limits without having to use the epsilon delta type argument. The limit of 5 as x gets really close to 2. What does 5 get close to? 5. Just hangs around at 5 all day long. As x gets really close to 2, what does x get really close to? 2, yeah. And as, no, that's not what I wanted. Revise this today. As x gets close to 2 is what I meant to say. Then x cubed gets really close to what? It really gets close to 2 cubed, which is 8, yes.
Wouldn't as x gets close to x just mean that the function doesn't work?
It just means it's a typo.
No, yeah,
In general, x gets close to x. Really wouldn't say that. Just not a lot. If the values were different, we could make some sense out of it, but I just don't think I can make sense out of that. Yeah. Some typos you can make sense out of, but not that one, I don't think. All right, so we want to look at some techniques where if we evaluate the limit of some complicated looking expression, we can break the expression down and express the limit of that expression in terms of limits of some of its components. If it's the sum of expressions, if we could say the limit of a sum is equal to the sum of the limits, that would be great. If we can write a more complicated expression as the product of simpler expressions that we could handle a little bit better. If we could say the limit of a product is equal to the product of the limits, that would be great. Well, we can just about say that in a lot of cases. Imagine that we have a couple of functions, and for each of these functions, the limit as x approaches c exists. Limit of f of x as x approaches c exists and equals L, and limit of g of x as x approaches c exists and equals k. Then we want to try to say something about the limit of the sum of those two functions, the limit of the difference of those two functions, the limit of the product, the limit of the quotient, and the limit of, and we can actually get this from the c part, the limit of an expression raised to the nth power, f of x raised to the nth power. The limit of the sum of two functions equals the sum of the limits of those expressions. I'm going to try a picture of this just to try to convey the idea. I hope I don't have to resort to the epsilons and deltas. So we've got I should keep it linear because I may not necessarily have to keep it all that linear. So we've got the function f, let's say in blue, and the function g, maybe in red if we can tell the difference. This could be tough. Think I could draw the graph of the sum of those two functions? Sounds like a job for GeoGebra, actually. Or even the graphic calculator. Maybe point by point I could give it a shot. Not a bad exercise, although technology will take care of this far more efficiently than we can do it. So if we've got a value here for the g function and a value here for the f function, we'd want to add those together. If we added those together, this and maybe that much more, this would be the sum. If we take this point and add those, I'm thinking maybe like that, something like that. If we take this and add it to that, maybe like that, and this and add to that, something like, I don't know, it's Yeah, something like that. That's kind of tough. Well, here we go. Let's pick a point there, and a point there, and a point there. X approaches C. Like this, and like this. X is getting really close to C. G of X, there's G right there. G of X. That's getting really close to... What's the limit of G of X as X approaches C?
Oh.
I guess the second one is K. And the first one is L right there. That's L. And basically what we're saying is that the sum function, whatever that looks like, probably doesn't look like that. The sum function is L plus K. It's getting close to, it's approaching L plus K. That was a little rough. I'm not going to attempt to draw the difference or the product or the quotient, but unless you're going to be terribly unsatisfied without the epsilons and deltas, I'm just going to say, with our intuition, if X gets close to C, f of X is getting close to L, G of X is getting close to K, so the difference of those two functions is getting close to the value L minus K. If the individual quantities are getting close to L and K respectively, then their product is getting close to the product L times K. If the individual quantities are getting close to L and K respectively, then their quotient is getting close to the value L over K, provided K is not 0. If K is 0, it's possible for a limit to exist and equal 0, but then this is not going to work if the denominator of this expression is equal to 0. Let's imagine that we believe the C part. If we believe the C part, that the limit of a product is equal to the product of the limits, we can actually use that if we assume n, if we're just saying n is a whole number here, to show this part. Because the limit of f of x to the nth power as x approaches c could be written as the limit of f of x times f of x times, I guess that's enough of them, put some dots there, times f of x as x approaches c. But what we're saying is the limit of the product equals the product of the limits. This is equal to the limit of f of x as x approaches c times the limit of f of x times x approaches c times a bunch of them times the limit of f of x as x approaches c. And how many of them are there? Well, they're n factors there. So they're n factors there. So this is the limit of f of x as x approaches c to the nth power. So the limit of expression raised to a power is equal to what you get when you evaluate the limit of that expression and raise it to a power. Now, this could be potentially helpful in a case where you've got some rough-looking expression, and I just don't think we're going to need this graph for posterity, so I'm going to get rid of it. Suppose we have the limit of 8x cubed minus 19x plus 40 to the fifth power as x approaches 2. Something like this. Well, what we're saying is this is equal to the limit as x approaches 2 of 8x cubed minus 19x plus 40 raised to the fifth power. This is, I think, kind of a good thing, because if we were stuck having to evaluate this, we would need to take 8x cubed minus 19x plus 40 and raise it to the fifth power. And that's a real pain. Take a trinomial, raise it to the fifth power. And then evaluate the limit as x approaches 2. What could be considerably simpler is to take just the 8x cubed minus 19x plus 40, evaluate that limit as x approaches 2, and then get a number and raise that to the 5th power. That's going to be an easier task.
And that works for the g of x too. You just use the s of x.
Absolutely. Absolutely. One more that works here, and let me put in x approaches c right there, and x approaches c right there. Limit, and this might be one of the more important ones here, the limit of a constant times a function. The constant, we're going to use this all over the place. That constant can be passed through the limit. If the constant doesn't change when x changes, then that constant can be passed in and out of the limit. We can't take x or some expression with an x in it and pass that in and out of the limit, but we can do it with the constant. It's a constant factor. And you can kind of see this if we believe the limit of a sum is equal to the sum of the limits. Suppose we have, and here I'm kind of assuming k is a whole number for simplicity. Suppose it's the limit of, well, k times f of x as x approaches c. That's the limit of f of x plus f of x plus dot 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 plus f of x. K terms there of f of x, or k times maybe, equals the limit of f of x as x approaches c right there, plus the limit of f of x as x approaches c, plus dot dot dot, plus the limit of f of x as x approaches c. There are k of them, so it's k times that. Yeah. So it's not this, it's not that, it's this. Okay, and we'll use that just right away here. Example 1. Now example 1, I'm a little bummed that we already have a theorem to deal with the x cubed. I'm going to pretend like we didn't see that theorem at the top of the notes here. This is a polynomial. Polynomials are nice, and our next theorem tells us, or affirms for us, that polynomials are nice functions. It's we haven't defined what it means for a function to be continuous, but this is a consequence of the fact that polynomials are continuous functions everywhere. What we'll do in the future, after this example, is my definition of the future, is we will evaluate the limit of a polynomial by substituting the number for x, just like that. But here's one example where we won't do that. We'll use the theorems that we just looked at. First, I want to use the theorem that the limit of a sum is equal to the sum of the limits. Limit as x approaches 2 of x cubed plus the limit as x approaches 2 of 3x plus the limit as x approaches 2 of 9. Now at this point we can actually take the 2 and substitute it for x. In fact, we did that very problem, didn't we, at the top of the page? Where was that? Was it there? Yeah, there it is. Let's not do it that way. Instead, what I want to use is the limit of an expression raised to a power is equal to the limit of that expression raised to a power. Basically, instead of x cubed, I want to calculate the limit of x as x approaches 2 and cube that. It's just an extra step here. And this one, I can actually use this very last one, limit of k times f of x equals k times the limit of f of x. Could use that and take the 3 and pass it through the limit and write it like that. And we can go ahead and evaluate the limit of 9 if you like. As x approaches 2, what is 9 approaching? 9. Limit of a constant equals that constant. And now we use the limit at the top of the page. Was it there or was it there? it was there. The limit of x as x approaches c is going to be c. So take the 3 and substitute it there. This is equal to 3. And this is going to be, wait a minute. What in the world did I do? Sorry. 2. Limit of x as x approaches 2 is equal to 2. As x approaches 2, x approaches 2. Just like that. And then we multiply that by 3 because 3 is the factor out in front. Here, as x approaches 2, again, x approaches 2. And in this case, we take the 2 and cube it. Now, we'll never again evaluate the limit of a polynomial by doing all these steps. This is ridiculous. But it does emphasize the particular theorems that we have involving limits. We might have to deal with more complicated functions than polynomials and use some of these same theorems to evaluate those limits. But in practice, we take the 2 and we cube it. We take the 3, multiply by 2. We take the 9, and there we go. 8 plus 6 plus 9 equals whatever 14 plus 9 is? 23. There we go.
So 23 is the limit, right?
So 23 is the value of the limit, and 23 is what you get when you take the 2 and just plug it in. Yeah.
So I'm assuming we're not supposed to just plug 2 in. We have to show the work this way.
From now on, now we're in the future. This is after this particular example. Now we're in the future. From now on, it's okay just to take the 2 and plug it
Now that we know why.
in. Exactly. Now, not for all functions, but for polynomial functions, we can do that. Right. We have a theorem about polynomials, and it's extended to rational functions. Rational functions are those that can be defined as a polynomial over a polynomial, so long as the polynomial in the denominator is not the 0 polynomial. Limit of a polynomial function as x approaches a is equal to what you get when you evaluate the function at a, p of a, basically. And if you have a ratio of polynomials, p of x over q of x, and you want to evaluate the limit, and the limit of the denominator, whenever a is not 0, no, that's not what I meant to say. What I meant to say was whenever q of a is not equal to 0. There we go, that's better. The limit of p of x over q of x is equal to p of a over q of a, provided q of a does not equal 0. So applying this theorem means if we want to evaluate the limit of x squared plus 4x plus 5 as x approaches 8, all we need to do is substitute 8 for x. And so it's 8 squared plus 4 times 8 plus 5. And that's, what is that?
37 plus 64.
101. So 101 is the value of this limit. For the other one, it's a rational function, and just a quick look at the denominator. 3, when substituted into the denominator, does not make the denominator 0. So we can say this is 3 squared plus 2 times 3 plus 1 over whatever 3 minus 1 does equal.
8.
9 plus 6 plus 1 over 2. 16 over 2 is 8. There we go. So polynomials and, for the most part, rational functions are very nice in that wherever they are defined, their limits are equal to their values. When we get to continuity, basically we're saying these functions are continuous wherever they're defined. Textbook just throws this in. It turns out to be a pretty useful limit, but it throws it in without a great deal of proof. Let n be a, okay, I've got some proofreading to do. Let n be a positive integer. There we go. Positive integer. The following limit is valid for all c if n is odd. Limit of the nth root of x is equal to the nth root of c. If you just want to consider the square root function, 0, 0, 1, 1, 4, 2, if I quite the good enough, I guess. And that point's a little bit too high. Nope, I don't like it at all. That should have been flatter, and that not quite so steep. There we go. Let the square root function. What's the limit of the square root of x as x approaches 4? Well, there's 4. As x gets really close to 4, then the square root of x is getting really close to what number?
2.
2. Yeah, and in fact, when it gets to 4, it actually equals 2. So the value of this is the square root of 4, which equals 2. So not a really surprising theorem there, but it works. Limit of a composite function, or the composition of two functions, is pretty powerful, particularly when the function g is kind of rough. If we want to evaluate the limit of f of g of x as x approaches c, and we don't want to actually have to take the time to compose them, actually to calculate that f of g of x. If the limit of g of x as x approaches c actually exists and equals L, then what we can do is evaluate the function f at that answer, whatever we get, and that will be the value of the limit, f of L. I actually did put together a little GeoGebra app for that one, GeoGebra worksheet. See what I called it. I think I called it limit of a composition good. I had a previous attempt at that was not good, but hopefully this one will be. So we've got a couple of functions here. In fact, the example, next example is the one that this is intended to help us with. Let's consider the polynomial function f of x equals x squared minus 2x plus 5, and g of x is the function we actually looked at last time. This was the one where as x got really close to 2, the numerator got really close to 0 and the denominator got really close to 0. But the ratio of the numerator to the denominator was well, approached an actual number. Do you remember what the value of that limit was? What did we say last time? Of the limit of 3x minus 6 over the square root of 4x minus 4 minus 2 was as x approaches 2? I believe we found it was equal to, was it 3 or was it 3 halves? Was it 3? So we found that last time. Based on the graph that we looked at, it looked like the y value was getting really, really close to 3 when x got really, really close to 2. So we're going to take this as the limit. We'll see algebraically a few examples down exactly how to do this without having to resort to the technology. But if we were going to try to find the limit of f of g of x as x approaches 2, one approach might be to try to simplify the expression f of g of x. And that would be kind of a pain. We'd have to take this expression and put it in there, and then put it in there, and then simplify all that. And even when we do simplify all that, I don't think it would be at all obvious what the value of that limit ought to be. But if we know that the limit of g of x as x approaches 2 actually exists and equals 3, we can apply this theorem and say this is basically, because f is a continuous function, it's a polynomial, so it's a really well-behaved function, continuous function, we can pass the function f through the limit and say this is f of the limit of g of x as x approaches 2. And so it's f of 3 which is 3 squared minus 2 times 3 plus 5. 9 minus 6 plus 5, 3 plus 5, and it equals 8. So x gets really close to 2, and this rough looking expression here gets really close to 3 in the process. But all the while, we're taking the function f and evaluating it at whatever g of x gives us. So if the values that g of x is giving us are getting really close to 3, then what f is doing is turning those numbers into numbers that are really, really close to 8. Now what the GeoGebra worksheet does is try to show you where the values are going and where they're coming from. So imagine that we start with a and we're going to approach 2. The blue graph is the one that we looked at last time. It's kind of flattened a little bit, but it's the top half of a parabola there. And it's the 3x minus 6 over the square root of 4x minus 4 minus 2. That's what the blue graph is. So when evaluating the composition, that's the function that gets evaluated first. So we take numbers that are approaching 2, like 1. We take the number 1, and we evaluate the blue function, and we get something. We get about 1.4. Well, then we had to take that 1.4 and evaluate the red function. Well, let's see, there's 1.4, and so it sends us to 1.4 there, back to the x-axis again. And so we take the red function and evaluate that at 1.4, and it gives us this particular value. So I suppose I could have named that somewhere. F of g of x equals whatever it is. So let's see, I could say, I'm going to have to give that a name, f of g of x. What's it going to call it? It's going to call it p. Well, that's nice. It actually does the composition there for us. So let's see what we've got there. Just 1 second. So f of g of x, g of x, and I'm going to link this to p of x. And I want that actually, how about p of a? Put that right at the bottom. Call it I. So let's do this. I'm leaving it to me. All right. Let's approach 2. We've got A. A is getting really close to 2. And there's the A value. And A is about 1.5. If we take 1.5 and evaluate the blue function, we get about 2.5. 2.5, send it back to the x-axis, evaluate the red function, and we get about 6.3. as we let a get closer and closer to 2, what's happening is the blue function is giving us values closer and closer to 3, and then values closer and closer to 3, the red function is giving us values closer and closer to 8. So when it gets to 2, it's going to disappear. Yep, there it's gone, because the blue function is not defined at 2. It's undefined at 2, but as x gets really close to 2, it's getting really close to 3. So we can actually evaluate the function at evaluate the red function, the polynomial function at 3, and take care of that. Not do what I wanted to do, sorry. But the original idea hopefully would have worked okay. We don't need the p function either. Get rid of that. Yes.
Well, back to our not this GeoGebra thing, but on example 3, when exactly is 3x minus 6 over the square root of 4x minus 4 minus 2 equal 3?
The limit, we did that last time, and we're going to do it again today, but let me see. Let's see, rotate clockwise, clockwise, clockwise. Yeah, that was the example we started class with last time, and it was yeah, it's example 1 right there. I'm just trying to see where I actually wrote that down. I guess I showed it out, but I never actually declared that it was equal to 3 because as x got really close to 2, that point there, 3, 2 there, 3 there. We did it kind of graphically rather than algebraically, but that's the conclusion we reached. The value of that limit was equal to 3. Transcendental functions. We're going to take it as a given that the limits of the sine, cosine, tangent, cotangent, secant, and cosecant, because of what we know of their graphs, how their graphs behave from trigonometry, that wherever they are defined, if x approaches a number in their domain, the limit can be obtained by evaluating that particular trig function at that number. So if I want to know the limit of sine x as x approaches pi, all I have to do is find the sine of pi, and that will give me the value of the limit. And the same for the others. If it's a place where one of these trig functions has a vertical asymptote, then we're not saying the limit exists. It's just simply for c that's in the domain of the given trigonometric function. All right. So for example 4. The limit as x approaches 2 of the sine of pi times x minus 1 over 4 is going to be, well, we could look at this as a composition of functions, but basically we have a polynomial function, pi times x minus 1 over 4, and then we have the sine function that's composed with that. So this is going to equal the sine of the limit of pi times x minus 1 over 4 as x approaches 2. So this is the sine of pi times 2 minus 1 over 4. This is the sine of pi over 4. What is the sine of pi over 4?
45 degrees.
Sine of 45 degrees would be at the square root of 2 over 2.
Yeah.
45-degree angle there. So 1 square root of 2. So 1 over the square root of 2, or the square root of 2 over 2 if you like rational denominators. So that would be what you'd get. Limit of x times the cosine of x as x approaches pi. We had a theorem up above that said the limit of a product is equal to the product of the limits. So this equals the limit of x as x approaches pi times the limit of cosine x as x approaches pi. Well, as x approaches pi, x approaches pi. So this value of this limit is pi. And the limit of cosine x as x approaches pi is the cosine of pi. What's the cosine of pi? It's over here, right?
Yeah, negative 1.
So -1, 0. Cosine is -1. So negative pi is what we're looking at for this limit. Now the last one, a similar statement can be made about exponential functions and logarithmic functions. Any number in their domain, the limit can be calculated just by evaluating the function at that value it's approaching. So the limit of the square root of the natural log of x as x approaches e to the 4th power equals, well, we have a theorem about radicals. The square root of the limit of the natural log of x as x approaches e to the 4th power. So I'm simply going to evaluate the natural log at e to the 4th power. So the natural log of e to the 4th power is the power that e can be raised to get e to the 4th power as the answer, which is 4. And the square root of 4 is 2.
Gotta remember your algebra.
Yeah. Those dreaded logarithms. Functions that agree at all but one point. Yeah, this is the section that never ends, by the way. Not every section in this textbook will be this lengthy, but this is the section that never ends. Just theorem after theorem about limits. Functions that agree at all but one point. We have two functions, f and g, and there's an open interval containing c. I think this picture should work out better than some of the pictures I've drawn today. So there's c, and here is an interval, open interval, containing c, and we need a bright blue function, something like that. And how about a red function? Something like that. So a bright blue function and a red function. F, whoops, let's call this G and call the blue function F. Like that. They agree. They have the same value everywhere in the interval except possibly at C. We don't know what's going on at C. So let's put a circle there. Maybe they agree. Maybe they're both defined but have different values. Maybe they're both defined to have the same value, but it's not that value that we expect it to be. Doesn't matter what's going on at C, but in an open interval containing C, they agree. Well, the limit of f of x as x approaches C is equal to the limit of g of x as x approaches c. That's the conclusion. The two functions must have the same limit if they agree on an open interval containing c. So basically what we do is this. This is used for indeterminate forms. I mentioned this last time, and we'll continue to talk about indeterminate forms. The most popular indeterminate form that that we'll look at is 0 over 0. Basically, the numerator is approaching 0 and the denominator is approaching 0. And the ratio of the two could be approaching most anything. It could be approaching 0. It could be going off to infinity. Or it could be approaching some finite real number other than 0. So, so we use this to take this expression, x squared minus 3x plus 2 over x minus 2, and find that it's equal to some other function, some other expression, that that doesn't go to 0, whose denominator does not go to 0 when x approaches not 3. Yeah, it's supposed to be a 2. Huh. You know, I go years without revising my notes because when I revise them, I make mistakes. I correct the mistakes, and then I think, oh wow, mistake-free notes. Who would have thought it? Let's say x is approaching 2. If x is approaching, no, it wasn't a mistake. It was deliberate. It was deliberate because if I change that to a 2, then it's the same as part B. The denominator is not approaching 2, so all we have to do is plug in the 3. 3. So it was. I thought I made a mistake, but I was wrong. I was mistaken. 3 times 3 plus 2 over 3 minus 2. This is 9 minus 9 plus 2 over 1, which equals what? 2. Okay. Yes.
Would it be okay if you factored the top and then the bottom? Because if you factor the top polynomial, you can cancel out the x minus 2.
Absolutely. In fact, we will do that. We will do that in the B part. The point is, we don't have to do that in the A part, but we kind of do have to do that in the B part. The B part, if we look at this, I'm not going to say it's equal to 0 over 0, but if we make the observation, if you evaluate this thing at 2, the numerator, 2 squared is 4, 3 times 2 is 6, 4 minus 6 is negative 2, and negative 2 plus 2 is 0. So the numerator is approaching 0 as x approaches 2. The denominator is approaching 0 as x approaches 2, so it's an indeterminate form of type 0 over 0. So what we want to do is come up with a function that agrees with this function, well, basically everywhere except possibly at x equals 2, where this one's undefined, but this other function won't be undefined at 2. And we factor. This is the limit as x approaches 2 of x minus 1 times x minus 2 over x minus 2. This is equal to the limit as x approaches 2 of, and here's where we're actually using this theorem. X minus 1 times x minus 2 over x minus 2 is equivalent to x minus 1 because they have exactly the same value for all values of x for which they're both defined. It's just that the top one is not defined at 2 and the bottom one is defined at 2. That's the only difference. But you pick an x any x other than 2, they'll have exactly the same value. If we pick x equals 3, for example, and we plug 3 into this one, we get 2. If we plug in 3 into this one, 3 minus 1, we get 2. So they have the same value for that value of x and for all other values of x except 2, the number 2. But the top one's not defined at 2, but this one is. So now we plug in the 2. 2 minus 1 equals 1. So if there is a factor of the numerator and a common factor of the denominator that's driving both the numerator and denominator towards 0, if we can factor that factor out of both the numerator and denominator and then divide them out, then it may be that neither the numerator nor denominator has to go to 0, but we can come up with well, not an indeterminate form, but a real number that is the limit. Youch. Does 1 make the numerator 0 in this next one? Yes.
So, like on problem B,
like,
can we always factor it out and change it?
Yes, when you're evaluating limits, yes, that's going to be.
Well, like if we factor it out, will it always work in the Like once we get it down to x minus 1,
Mhm.
the limit will always plug in and work.
Yes, according to the theorem,
Okay.
it will work. And I didn't prove the theorem, but I believe it nonetheless. So yes, it will. It'll always work. Can you factor 7x cubed minus 26x squared plus 29x minus 10? With a little help from our calculators, I think we can maybe do this. Let's graph it and look for x-intercepts. That's my first thing that I suggest my pre-calculus students do. Graph it and look for the x-intercepts. What am I doing there? I want y equals. Clear that. 7x cubed. Minus 26x. Now, we don't want to waste a lot of time. We ought, I'll admit that I designed this problem with the intention that if you substitute 1 into the numerator, it should make it 0, and that when you substitute 1 into the denominator, it should also make that 0. We should confirm that, though, before we waste too terribly much time with this. I'm going to zoom 6 and see if we do get an x-intercept at 1. Looks like maybe. Second calc value, substitute 1, and yes. 1 does make the numerator 0. I'm going to deselect it. I still don't want to waste a lot of unnecessary time factoring this if we don't have to. It's only going to be a problem if it makes the denominator 0. So let's see. 7x cubed plus 16. And again, that was my intention, but you never know when I'm making out these notes how it's going to work out. 43x plus 20. Let's graph that. Again, do we get an x-intercept at 1? I think maybe. Second calc value 1. Yep. So 1 makes the numerator 0, 1 makes the denominator 0. Now, at first, it just seems like that's really frustrating because it means this is an indeterminate form. But it's a valuable piece of information because according to the factor theorem, if 1 is a 0 of a polynomial, then what binomial is a factor of that polynomial?
X minus 1?
X minus 1. So with a little synthetic division, we can take a few constructive steps toward factoring this. So if we want to, if we realize 1 is a 0, we can divide this by x minus 1 using synthetic division. Let's do, well, 1 is a 0, both of them, so I'm going to do them separately. Let's try the numerator. 7, negative 26, 29, negative 10. Bring down the 7. And how do we do this? Multiply
Multiply.
and add. And multiply and add and multiply and add. So 1 times 7 is 7, and we add to get negative 19. 1 times negative 19 is negative 19. We add to get 10. 1 times 10 is 10, and we add to get what better be 0. If it's not 0, something has gone terribly wrong. So we can now factor the numerator. This is the limit as x approaches 1 of x minus 1. That's the factor because 1 makes it 0. And the other factor is 7, negative 19, 10, 7x squared minus 19x plus 10. So that's a big time step because we're more comfortable factoring quadratics than we are factoring cubics. Do the same thing with the denominator. Trying to put it maybe to the side of it so we don't get them mixed up. I probably should be color coding it, but I'm not. 7, 16, negative 43, 20. Bring down the 7, and then 20. There we go. So x minus 1 times 7x squared plus 23x minus 20. Now, if factoring trinomials is not your idea of a good time, there is a chance that each of these could have another rational 0. We could use the rational zeros theorem or just hope for an integer. I'm gonna hold out hope for an integer. Do you believe, this is the denominator here, do you believe negative 4 might be a 0 of the denominator? Possibly. Second calc value, 4.
-4.
Oh, sorry, thank you. -4. That's better. 0. So take this one and apply synthetic division one more time with -4. Bring down the 7, that's -28. This is -5, that's 20. So how about the limit as x approaches...
-4.
why am I putting us through all this? Of course you could do this, but if we want to know the limit as x equals 1, let's just divide out the x minus 1s and substitute 1 for x. I mean, this is not wrong, but it's not necessary to do the 7x minus 5. So this is the limit of 7x squared minus 19x plus 10 over 7x squared plus 23x minus 20. And do you suppose 1 is going to make the denominator 0? I don't think it does. This is going to be 7 times 1 squared minus 19 times 1 plus 10 over 7 times 1 squared plus 23 times 1 minus 20. Looks like -2 over 10. -1/5. Yeah. So the big thing there, really, once we were able to get the x minus 1s factored out, there wasn't a lot more work to be done. Divide out the x minus 1s and then apply the synthetic division. Time is up, it looks like.